Welcome to the Chemistry, Biology and Math Revision Hub. Today we'll be discussing the Pearson Edexcel International A Level Chemistry Unit 5 for January 2021, Section B. I will put the link to the Section A as well as Section C of this paper in the description box. So I will go straight to the first question. The first question here is question 19. It says, the diagram summarizes some reactions of copper compounds. Again, remember here we're looking at copper, so they've given us copper sulfate here reacting with potassium iodide to give us copper 1 iodide. And here we have sulfuric acid to give us a pink solid. If there is anything to do with copper, the chemistry of copper, and you see a pink solid, that should be the solid of copper. And then here plus a blue solution. A blue solution could be hexa aqua, copper 2. And then on this side, we have copper reacting with ammonia to produce a pale blue solid. If it's a pale blue solid, this is going to be a deprotonation reaction. And then here we see a black solid, that is copper. Copper oxide, which is copper 2 oxide, the black solid. And finally, here we have the blue solution, which could be hexa aqua, copper 2 plus. However, you may not be able to decode the right things initially as you look at the flow chart here. However, when you go through the questions, you could be able to understand fully. So here, if we have if we have a black solid, which is copper oxide, at least any student should know that this is that, and that is the pink one. If there is a blue solution after reacting with an aqueous sulfuric acid, that should be the copper, of course, copper hexa aqua, copper 2 plus, that is that complex. Another thing you need to know is when you see a dark blue solution, in your textbook sometimes they say the blue solution, that is because a ligand substitution reaction has occurred. So we have produced basically ammonia ligands have been attached to the sample we're looking at. So this one here is going to be ligand substitution reaction to that. And then this one here should be, if you have copper 1, converting it to copper 2, that could be oxidation. So when we go down here, they say identify by name, including the oxidation state or formula, the species in the sequence of that contain copper. So I will begin with P. This is guaranteed the pink solid should be copper, so the answer here should be copper. And then the blue solution should be hexa aqua, copper 2 plus. The reason for that is this is an aqueous acid when you react it with copper iodide. And you have to know a reaction takes place generating the copper 2 plus in aqueous solution. So the ligand, water ligand surrounded, that is going to be hexa aqua, copper 2. Then when we come to R, the pale blue solution when ammonia reacts with copper sulfate, aqueous copper sulfate, that is going to be due to deprotonation. So it should be 2 water ligands are going to lose their hydrogens to the ammonia, creating ammonium as well as this complex. So that is correct. And then we go to S. S is the black solid, that is guaranteed it's going to be copper 2 oxide. And then T, let me see T here. This reaction here is going to give away what T is. This is a ligand substitution reaction, so it should be tetraamine, copper 2. And then V, let's see here, V, copper 1 iodide reacts with ammonia, is still copper 1. So it should be, of course, diamine, copper 1, which we have here. And lastly, W, the blue solution. When this black, you remember here we have copper 2. When it reacts with an acid, the copper 2 plus ions are going to be released and the water ligands will surround it, producing the hexa aqua copper 2, which is that. So then part B says, T and V are the same type of chemical species. Name this type of chemical species. Since they say T and V, these are complexes. So it's a complex. I will go to the next part. It says, explain why T is colored while V is colorless. In transition metals, remember V, if it's colorless, is going to be copper 1. It means that the orbitals, when they are split, they're not partially filled for the electrons to be able to transition, while in T, they are partially filled the orbitals, so transition can occur. So I said, color formation among transition metal ions arises due to transition of electrons from lower to higher orbitals due to energy absorption after splitting the d orbitals. And again, remember, ligands approach the central metal, they split the d orbitals into lower and higher energy level orbitals. Then the electrons in the lower energy level orbitals can absorb energy and transition to higher energy level. And when that occurs, a color is going to be observed. So the next part I say, so here I said orbitals due to energy absorption after splitting of orbitals. So here we see the T, which is copper 2 plus, has partially filled the orbitals, which allow D to D transition of electrons. Hence, color is going to be observed. This is the reason why color is observed. And then V, which is copper 1, has fully filled the orbitals. It's 3d10, so there is no space for these electrons to transition, even if the ligands have split the d orbitals, so color is not observed. So Roman 3 says, suggest an explanation for the change of V into T on shaking. When you change V into T, and again to take you back slowly, remember V is diamine and T is tetraamine. Remember this is 1 plus, 2 plus. That is oxidation. If copper 1 becomes copper 2, it is oxidation. So I say copper is oxidized, copper 1 is oxidized to copper 2 by oxygen in air upon shaking. So that is how you get the 2 marks. And down here we have, they say the reaction between copper 1 iodide and sulfuric acid is a disproportionation. Write the ionic equation for the disproportionation reaction. State symbols are not required. So in this disproportionation reaction, we can see that copper is going to be converted into copper 1 here is going to be converted into copper 2 as well as copper solid. And the iodide is going to be, of course, there is nothing that changes in the iodide, it's still iodide. So what you would summarize is going to be this. 2 copper 1s, 1 is going to be oxidized to form that, while 1 is reduced to form that. So that is the disproportionation reaction. So either that or that can be acceptable. Next, they say show that the reaction in C1 is thermodynamically feasible. Use standard electrode potentials of the relevant half cells from the data booklet. From the data booklet, again, this is a disproportionation reaction. I have to get 1 for reduction and 1 for oxidation. These are respective electrode potentials. And it means since I want to carry out disproportionation, this reaction has to be reversed because both reactions have to be copper 1 giving me either copper, like this one, or copper 1 giving me copper 2. So it means this has to be reversed and be oxidized to generate electrons. So when I say E theta for the cell should be E right, this is going to be the E right and that is going to be the E left. And when I subtract the 2, I get a positive 0.37. Since this is positive, the E theta for the cell is positive, therefore this reaction will be feasible. I will continue on to the next part. Part D, the rare mineral, here we have this has the chemical formula that, so they say 4.26 grams of this mineral was dissolved in distilled water and the solution made up to 250 centimeters cubed. So this is kind of making a standard solution. Excess potassium iodide solution was added to a 25 centimeters cube portion of this solution and the iodine formed was titrated against a solution of sodium thiosulfate with a concentration of 0.0500 mole per decimeter cube. This procedure was repeated until concordant results were obtained. The mean accurate titer was 26.65. That is for the thiosulfate. So as you can see here, again to make it more observable, we can see here the concentration of the thiosulfate and the volume are there. So since I have all that information for thiosulfate, I'm going to use it to find the number of moles of thiosulfate first. So moles will be concentration times volume. That is the concentration. The volume in centimeters divided by 1,000 to convert it to decimeters. When you multiply that and that, it gives us this as the answer. So those are the number of moles of the thiosulfate. Now, when we look at this reaction here, the mole ratio of thiosulfate to iodine is 2 to 1. So if I find the moles of iodine, they're going to be a half the moles of thiosulfate, which is a half times that, giving me this whole thing. So here I did not multiply it. I just carried it forward. Now that we know, remember again, they took 25 centimeters cube proportion. So it means if the portion taken was 25 centimeters cube, it contained these moles of iodine. However, we need to find the moles that were contained, the moles of copper that were contained in that same portion. So after getting this iodine, we can use the mole ratio of iodine to copper. It's 1 to 2. So the moles of copper are going to be twice. Copper 2 plus are going to be twice the moles of iodine. That's what I did here. And I got that answer. So these are the moles of copper 2 plus in the 25 centimeters cube proportion that was used. And now we can scale back by multiplying that times 10 to find the number of moles present in the 250 centimeters cube. So when I multiply by 10, I get that. Now we know that the moles, we can find the molar mass. Molar mass of the whole thing is going to be mass divided by number of moles, which is the mass we're given. The number of moles is here. We can be able to find the molar mass, which is 319.70. Now, since we are looking for the value of N, we can use our periodic table to find this amount here. Potassium is 39.1 times 2. Copper is 63.5. 4 chlorine is going to be 435.5. When we add up this, you could subtract this total from that and get what 18N equates to. So 18N will give us 36 if you subtract, and then N comes out as 2. So the formula should be, if I can write it, should be K2CuCl4 2H2O, something like that. That should be the answer. So this brings us to the end of question 19. I will go on to question 20. Question 20, the question says, ketones are used for studying compounds in organic synthesis. This question is about butanone. The mass spectrum of butanone has significant peaks at mass to charge 43 and mass to charge 57. Give the structures of the species responsible for these two peaks. So I chose this part here is 43, and that part here is 57, as well as this part here is 57. So for me, I chose this part here. You can see CH3, CH2 that, as well as this part here, which is 43. So you can see that. So a mass to charge 43 and mass to charge 57 is going to be that. So I will continue to the next part. It says, give the structure of one other species that you would expect to produce a peak at a different mass to charge value in the mass spectrum of butanone. Others could be a CH3 at 15, a CH3-CH2 at 29, and this one here at 72. So any of these would be a perfect answer if you had written them. I will continue to the next page. They say, devise a reaction scheme to prepare propan 1-ol from butanone using no more than 4 steps. These reaction schemes are really very important. They say identify the reagents and essential conditions for each step and give the name or structure of each of the intermediate compounds. Remember, we are beginning from butanone. So with butanone, and since we want to prepare propan 1-ol, it means we have to cut down on the carbons. So with butanone, I can react it with iodine in the presence of sodium hydroxide to produce a triiodomethane and a carboxylate salt. So here it means I have cut off 1 carbon, so there is potential for me to make a propan 1-ol. In the next step, I'm going to use this and react it with sulfuric acid so that I can convert this carboxylic salt into carboxylic acid. This is what you can call a conversion of a carboxylic salt to carboxylic acid by reacting with an acid. So I will distill here and produce this carboxylic acid. And since I have a carboxylic acid, which is propanoic acid, I will just reduce using LiAlH4 in dry ether and then reflux. And this is going to be my final product. So I said, react butanone with iodine in the presence of sodium hydroxide to form sodium propanoate and triiodomethane. This is decreasing the carbon chain. Then add sulfuric acid to the sodium propanoate in order to convert it to propanoic acid and distill to obtain its pure form. You want to have purity and then reduce the formed propanoic acid using to propan 1-ol, refluxing using this reducing agent in dry ether. Every time you use LiAlH4, you have to use dry ether because if you use conditions that have water, this could react with the water and if you cause different reactions to occur instead of a reduction reaction. So let's go to the next page. Here they say, devise a reaction scheme to prepare 2-methyl-butene from butanone using no more than 4 steps. Again, this is a reaction scheme. And then they say, identify the reagents and essential conditions for each step and give the name or structure of each of the intermediates. Since they want us to prepare that from butanone, I went on to using Grignard's reagent pathway. So we will begin with this one here. Remember this other part, the methyl part. I wanted to be able to introduce the methyl part. So CH3Br, when you react it with magnesium, you produce Grignard's reagent. And then Grignard's reagent is going to be reacted with a ketone. When we react it with a ketone, we will produce This alcohol here is a tertiary alcohol. When you produce this tertiary alcohol, and then later on we could dehydrate it, take away water. So this tertiary alcohol, and in the next step we use phosphoric acid to dehydrate the tertiary alcohol, meaning we are taking away a water molecule, and then we produce our alkene we were looking for. So again, in writing, I said prepare Grignard's reagent using CH3Br and magnesium powder in dry ether. That is important. And then react the formed Grignard's reagent with a ketone, here butanone, to form a tertiary alcohol, which is that. And then we'll use concentrated phosphoric acid to dehydrate the alcohol and convert it into the alkene we were looking for. I hope you understood that. This brings us to the end of question 20. Let us go to question 21. Question 21. A yellow crystalline solid E dissolved in distilled water to give a yellow solution. Addition of dilute sulfuric acid to the solution produced an orange solution. So this is a giveaway. If you have a yellow turning orange when an acid is added, it should tell you that the yellow is chromate 6 and the orange is going to be dichromate 6. So when we go on, warming F with ethanol resulted, remember F is, we assume is the dichromate. Warming F with ethanol resulted in a green solution, G, and the formation of ethanol. That should be chromium 3. Ethanol is an aldehyde, so of course you can understand this is kind of a it's reduction of the dichromate 6 to chromium 3. So they say a standard cell was set up using solutions F and G, dichromate, as well as G, we have it here, the green chromium 3. Okay, for the right hand electrode, and ethanol and ethanol for the left hand electrode. So ethanol to ethanol, that is oxidation. So they say the E theta for the cell was found to be positive 1.94. This is the equation taking place for one of the half cells. Question A says deduce the formula of the ions responsible for the colors F and G using standard electrode potentials and E theta given and the data booklet. So if you refer to your data booklet, here we can see, remember here, I have already established that when you look at the data booklet, we're going to find the one for dichromate chromium 3. So the dichromate chromium 3 is going to be on the right because we can see it's going to be gaining electrons to be reduced, while the other is going to be oxidized. So the alcohol is going to be oxidized to an aldehyde. So it means it has to be on the left to be oxidized. So this is what we have there. So it should be on this side. Okay, so calculating the E theta should be the E theta right minus E theta left. Since we do not have this, but we have that, you can be able to calculate the E theta right, which is 1.94 minus this one. Remember, this is going to become positive. You take it the other side, it becomes a negative, and the value is going to be this. So this is going to be the E theta for the right half cell. You can see that. So also, when you look at the data booklet, the E theta for that specific half cell, the dichromate chromium 3, is going to be that. That confirms that G is chromium 3 and F is dichromate 6. So basically, you first calculate this and then refer to your data booklet, that value, if it corresponds to the half cell of dichromate chromium 3, then you can confirm. Next part, write the overall equation for the reaction in the cell. State symbols are not required. Now here we have to combine the two equations. Remember, one equation is given to us, it's here. However, to fulfill the reaction we have observed here, this equation has to be reversed because it is going to be oxidized. So I reversed it here, as you can see. I will reverse, I think here, we can see here, I reversed. The reason for that is to ensure that the alcohol is being oxidized to the aldehyde. However, before the reversal of the reaction, I first considered that the electrons are matching. Remember, each dichromate requires 6 electrons to be converted to 2 chromium 3s. It means if you consider the other equation whereby only 2 electrons are produced, we need to multiply the whole equation by 3 in order to generate 6 electrons required by this reaction. So to do that, I multiply this whole thing by 3, which gives us 3 that, 3 that, 3 that, 6 that, and 6 that. I hope you can see that. This equation is multiplied and it's reversed in this step. So when we come here to combine the overall, I'm going to combine this equation and that equation to get the overall equation, as you can see written here. This is the equation that we're looking for. The key thing was for you observing that in this equation, the alcohol should be the one to be oxidized. So reverse the whole equation and then multiply by 3 appropriately to ensure that the electrons are actually 6 as required. The electrons generated should be 6 because this requires 6 electrons for the reaction to proceed. Now, part C says, write the ionic equation for the reaction of the aqueous solution of E with dilute sulfuric acid. State symbols are not required. This is kind of easy. So here we see 2 moles of chromate 6. We react with 2 H pluses. This is the sulfuric acid producing dichromate 6, 1 mole, as well as water. So this brings us to the end of question 1. Let's continue on to question 22. This was question 21. Let's go to question 22. Question 22. Let's begin. Using excess oxygen, 25 centimeters cubed of a gaseous hydrocarbon was burned completely. After cooling to room temperature, the total gas volume was measured and found to be 75 centimeters cubed less than the total gas volume before the mixture was ignited. So they say when the product gases was shaken with potassium hydroxide. Potassium hydroxide actually absorbs carbon dioxide, so this is to remove carbon dioxide. So potassium hydroxide solution, the total gas volume decreased by a further 100. That means the volume of CO2 produced is 100 centimeters cubed. So let's see, they say all gas volumes were measured at room temperature and pressure. So it means, you guys know at room temperature and pressure, equal moles of gases, equal number of, basically gases that have the same volume have equal number of moles if the conditions are room temperature and pressure. So they said a general equation for the combustion of a hydrocarbon is as below. So you remember this burnt completely. How do we know? Because they used excess oxygen. Using excess oxygen was to ensure that the hydrocarbon burns completely, and if it burns completely, it will produce carbon dioxide and water. Everything occurred at room temperature. So the first question is asking, determine the molecular formula of CXHY. You must show you're working clearly. So one thing we can see here is 1 mole of this produces X moles of carbon dioxide. And since we are working at R, T, and P, we know that equal volumes of gases will have equal number of moles. So 25 centimeters cubed of the hydrocarbon should produce 25 times X centimeters cubed of carbon dioxide. That is guaranteed. However, after they used potassium hydroxide, we saw that the volume decreased by 100, meaning the volume of carbon dioxide was 100. Therefore, the 25X is equal to 100, as you can see here. And therefore, we can find the value of X as 4. Now that we have found the value of X, our next aim is to find the value of Y so that we can be able to predict the molecular formula of the hydrocarbon. Now we're going to use our next thing. Remember they said there was a decrease of 75. You can see this here. There was a 75 centimeter cube decrease. So for the next part, I went to change in volume. Remember they said there was a 75, sorry. It's okay. They said there was a 70. This is 8. It's not 9. I better let me try to make it so that you cannot confuse it. That was a 75 centimeter cubed decrease after the reaction. So it means the volume of the original hydrocarbon plus the volume of oxygen that reacted minus the volume of carbon dioxide produced should be 75. So in this case, we say if you have the original volume, which is 25, that is for the hydrocarbon, and the volume of oxygen, that is 25. Remember, if you're using 1 mole, X moles, 25 times that, 25 times X. So the volume of this should be 25 times X plus Y over 2. That is why I have that. That is the volume of oxygen that reacted, minus the 25X centimeters cubed of carbon dioxide produced should give me 75. So in the end, I observed that, remember again, the difference in the volume is going to be what we are looking for, which is 75 here. So simplifying, remember this is going to be 25. That is going to be 100 plus 25y over 4. And that is going to be 100 since we found that x was 4. This gives us 75. And then when we make y the subject, we end up with y is equal to 8. So in conclusion, since we found our X to be 4 and Y 8, the formula of this should be carbon 4, hydrogen 8. This was kind of easy, but it can be tricky, so you have to be very careful how you interpret the data. So part B says, when this hydrocarbon was added to a little bromine water and the mixture shaken, the bromine water remained yellow. Since the bromine water remained yellow, it means there is no carbon-carbon double bond. Because if there was a carbon-carbon double bond, then it could remain the same. Now, you guys, let me show you something here. If we know there is a compound that has carbon 4, hydrogen 8, but not alkene, meaning it doesn't have a carbon-carbon double bond, then it should be a cycloalkane, because cycloalkanes and alkenes have the same general formula. So it means they should be a cycloalkane. You can see here. So it could be that, or it could be that, like this structure here. It could be anything, basically. If you do like that, it could be any, but this and that are exactly the same. So you could say this or that. Because they said suggest two possible structures, I went with this, which is a cyclobutane, and this one here. So this brings us to the end of question 22. Let us move on to question 23. Question 23, it says, compare and contrast the mechanism of the action of platinum as a catalyst in the removal of pollutants from car engine exhaust fumes with that of vanadium pentoxide as a catalyst in the contact process for the manufacture of sulfuric acid. So when they say compare and contrast, we have to talk about the similarities as well as the differences. Similarities are both platinum and vanadium 5 oxide are heterogeneous catalysts. It means they are in different phase as compared to the reactants, and both enable the reactants to adsorb onto their surfaces for the reaction to occur. The differences are, first, we talk about the platinum in the catalytic converter. In this case, the platinum will provide a surface area onto which the reactants are going to adsorb, and when they do adsorb, a reaction will take place because adsorption of the reactant is going to cause, or reactants is going to cause their bonds to be weakened, and the reaction is going to occur at lower energy. When the reaction occurs on the surface of the catalyst, the products are going to be formed and they will dissolve off of the surface of the catalyst. So the mode of action is different. However, in the contact process, since in the contact process we have vanadium 5 as a catalyst, a reaction occurs like this. We have sulfur dioxide that is going to react with vanadium 5 oxide, producing vanadium 4 oxide, and then sulfur trioxide. And then the produced vanadium 4 oxide is going to react with oxygen, producing vanadium 5 oxide. So that is going to be it. So it means, you remember, the reactants are going to be, in this case, it should be that reacting with oxygen. However, this catalyst is going to be reduced in the process so that one of the products can be formed. And later on, this is going to be oxidized back to its original process. So here I said, in the contact process, with vanadium pentoxide is reduced to vanadium 4 when it reacts with sulfur dioxide, and the sulfur dioxide is converted to sulfur trioxide. Then the produced vanadium 4 oxide reacts with oxygen to get oxidized back to vanadium, so to its original form, basically, which is vanadium 5 oxide. So this brings us to the end of this part, which is actually the end of section B. Thank you for being with us. Please do not forget to subscribe. I will be putting the links to section A as well as section C of this paper in the description box. I'll see you all next time when we talk about another paper. Please do not forget to subscribe. Bye-bye.